Let's take a look at our first law, the law of sines. Now, you'll notice right away we're not dealing with right triangles. We're dealing with non-right triangles, labeling our angles with capital letters and our sides, corresponding sides, with lowercase letters. Now, the law of sines has two different versions. It has the version where the sides are on top and the sine of the angle is on the bottom. And they have a version where sine of the angle is on top and the side is on the bottom. When we use the law of sines, we only use two at a time. So we might use A and B, or A and C, or we might use B and C. It depends on what they give us and how to use that. To tie this into our geometry, we're looking at angle sides, or angle side angles, and we'll get into the side angle as well. But this is where we would apply something like the law of sines. Another way to put this is I need to know at least one angle and the side that goes with it in order to use the law of sines. And if I know two angles, I do know the third angle because I can use the fact that three angles of a triangle still add up to 180. So I want to take a look at an example here. I know angle C, angle B. Technically, I would also know angle A. But if I'm going to set up the law of sines, I'm going to use the one with the side that I know. So I'm going to use this one because I know those two things. And I'm going to set up C with the sine of C. Plug in what you know. I know side B is 27.4. The sine of B is 28.7 degrees. I don't know side C, that's what I'm trying to solve for. But angle C I have, it's 102.3 degrees. And it doesn't matter if it's obtuse or if it's acute, it should work. So if I solve this for C, I'm going to multiply by the sine of 102.3 degrees. And that gets my C by itself. So C is equal to 27.4 times the sine of 102.3 degrees divided by the sine of 28.7 degrees. Side C in feet is roughly 55.75 feet. Now, a quick, easy check when we're using the law of sines or any of the laws that we're going to deal with. My largest angle should definitely have my longest side. My smallest angle should definitely have my smallest side. So this is a reasonable answer. It's much bigger, but I'm dealing with a much bigger angle. And now I can use that to find the other side and the other angle. Another example, and I try to put in more of a real-world situation. I've got this tilted flag stick, and I've got its shadow down here. The shadow is 22 feet. The angle made with the flag stick is 43 degrees. And normally our flag would stand up straight at 90 degrees, but it's tilted by 8 degrees. So now we know that angle B is 98 degrees. So I have an angle and a side and an angle. Now you might be thinking, well, you don't have the angle that goes with this side, but I'm going to use what I know about about triangles, and I'm going to figure this missing angle. So I'm going to add these two things, and I'm going to take 180 and minus that 141. That missing angle is 39 degrees. So I know all three angles. I now know an angle with its corresponding side. So I'm going to set up C, and I'm going to figure out how tall this flagpole is, so I'm going to use A. Those are the two versions, or the two parts of the law of sines that I'm going to use. And I'm going to try to figure out how tall this flagpole is. So I'm looking for A. Plug in what I know. I know side C is 22 feet. Angle C is 39. I don't know side A, but I know that angle A is 43 degrees. And now I can solve that for A. Multiply both sides by the sine of 43. And side A is 23.84 feet, to get my label correct there. Which makes sense. 22 feet is a 39-degree angle. 43 is a little bit bigger, so side A should be a little bit bigger. The only other piece of advice I have with using the law of sines, if you're ever solving for a missing angle, remember to get that angle by itself. You're going to have to use an inverse sine at some point to tell your calculator that you want an angle and not a side.